Yeah, that's okay. Yeah, project 1 is officially due today. Yeah, Friday's okay, but don't expect to get it back before the test. Yeah. Okay, so if you have your project today, just put it in the folder, and I will grab it after class. In this class, we're going to learn some different notation for the derivative, and we're going to explain what the derivative represents in a variety of real contexts. Okay, so this section is very notation heavy. Stick with it, and all the symbols will become second nature eventually. So we'll start with a brief history lesson. Calculus was invented or discovered, depending on how you think of math as being invented or discovered, by Leibniz and Newton at about the same time, around 1660 AD. Completely separately and independently of each other, they invented the same thing. But they had different notations to describe what they were inventing or discovering. So Newton wrote the derivative of x squared plus 7 as x squared plus 7 with a dot over it. Okay, so if you wanted to take the derivative of a function, you would just write that function with a dot on the top of it, and that meant the derivative. We never see this notation. There almost no textbooks use it, but it is actually used in Europe a lot. So I met some people in grad school who wrote this, and I was like, what the heck does that mean? They had to tell me that it was the derivative. So Leibniz used a completely different notation, and he used a notation dy dx to represent the derivative of y with respect to x. So graphically, what does the derivative represent? The slope of a tangent line, thank you. So, and slope, in the previous courses, you always would have calculated as delta y over delta x, right? That's a really common notation for slope. So dy dx is a way of saying this is a slope of a tangent line, but we're using a really, really, really infinitesimally small interval for calculating that slope. So instead of putting delta y over delta x, we write d. Like when you take the limit, that delta turns into a d. So that is really helpful in terms of thinking about units, because the derivative always has y units over x units because it represents a slope, small change in y over a small change in x. So about a century later, French mathematician Lagrange, he invented the symbol with the prime to be f prime of x for the derivative. So here are 4 notations that all just mean the derivative. F prime of x, d dx of something in brackets means the derivative of the thing in brackets, dy dx, and y prime. They all just mean the derivative of the function. One disadvantage of Leibniz notation, it's going to have some great advantages, but one disadvantage is that if you wanted to write f prime of 3, the derivative evaluated when x equals 3, in Leibniz notation, it's kind of awkward. We write dy dx and then a big vertical line that means evaluated at x equals 3. So that means take the derivative, then plug a 3 in, same as f prime of 3. Okay, so dy dx has units of the form y units over x units, because dy dx stands for the slope, a small change in y over a small change in x. So a small change in y is going to have the same units as y does. Small change in x is going to have x units. And if you're not using y's and x's in your particular problem, it is dependent variable units over independent variable units. So for example, if we have capital G equals f of t, it's going to represent the cumulative number of gallons of water that have passed over a waterfall t seconds after midnight. Then dg dt is going to have what units? Gallons per second. The g units is gallons, number of gallons, that's g. Right? And then the t units is seconds. So dg dt is going to be measured in gallons per second. And it makes sense because a derivative represents a rate of change. So this should look like some kind of rate. right? Gallons per second is the rate at which the water is going over the waterfall. So in the context of this example, what does G of 30 equals 120 mean? Yeah, so there are no derivatives in this sentence, right? This says after 30 seconds, $120 gallons have passed over the waterfall. What about dg dt evaluated when t equals 30 equals 3? What does that say? Yep, after 30 seconds, the water is going over the waterfall at a rate of 3 gallons per second. At t equals 30 seconds, the water is going over the falls at 3 gallons per second. Yep. Yep, you just need, but you do need to be able to sort of go back and forth. It would have been much easier to write g prime of 30 equals 3, yeah. So between time t equals 30 and t equals 31, in the next second, how many gallons of water do you think are going to go over? Gallons. 3 more gallons, yeah. It's going over, at this point, it's going over at 3 gallons per second. So if 1 second passes, we should get 3 more gallons going over the falls. Does that make sense? So we would have a cumulative amount of 123. If you know that you 120 had already gone over, the next second 3 more will go over, so you can have a new cumulative, you can estimate your new cumulative amount to be 123. Okay, now suppose R is going to represent dg dt, right? We already talked about dg dt. This is gallons per second. And now I'm defining a new function that's representing the rate R. The water goes over the falls. What are the units of dr dt? Yeah, gallons per second squared, or gallons per second, right? So the units on dr dt should be the R units, which I already said this is gallons per second, because R represents dg dt. So my R units divided by my T units is going to be gallons per second, and then my T units is seconds, gallons per second per second. Or some people who've taken physics might have seen gallons per second squared. It means the same thing. So that's kind of representing what? What is acceleration, the change in the rate of change? Yeah, how fast is the speed changing? Okay, so what does dr dt when t equals 20 equals -2 mean? Yes, at time t equals 20. At t equals 20, the speed of the water is decreasing by 2 gallons per second every second. So one small nitpicky thing is if you write decreasing, you don't put a negative on the 2, right? The negative means decreasing. So you could either say changing by -2 gallons per second or decreasing by 2 gallons per second. If you write them both, it's like using a double negative in an English sentence. All right, any questions? All right, so I have a bunch for you to do some interpreting.